Welcome to The Explainer. Today, we're going to completely demystify one of the most classic technical interview challenges out there, the longest palindrome problem. We are going to map out the exact evolution of its solution. So we'll start with a really basic, heavy brute force idea, and together, we're going to refine it into this highly optimized, incredibly elegant algorithm. So, right off the bat, how do you find a palindrome hiding inside another word without literally crashing your system? Now, if you're a software engineer, you already know that strict time and memory constraints are just a daily reality. You can't just throw unlimited computing power at a problem. When you're processing massive blocks of text, think millions of server logs or gigantic DNA sequences, inefficient string manipulation will absolutely devour your system's memory and bring the whole thing to a grinding halt. We need efficiency, and today we're going to build it step by step.
Okay, here's our roadmap for today. Number 1, the longest palindrome problem. 2, finding the inner palindrome. 3, the dynamic programming solution. 4, the optimized expansion approach. And 5, complexity and final trade-offs. Let's dive right in.
All right, Section 1, the longest palindrome problem.
Let's start by defining our core goal here. We're given a string, and our objective is to identify the longest palindromic substring hidden within it. So, for example, if our system is handed the string ABCCBAB, we need our logic to accurately extract ABCCBA. Now, to find the longest palindrome in a string like that, the naive thought, the easiest thing to do, is just to check every single possible substring. But generating all those possible substrings, that takes O and squared time. Think of it like this. You're pointing at the first letter, then scanning all the way to the end, then moving to the second letter, scanning to the end again, and so on. And then you have to read backward and forward through every single one of those generated substrings to check if it's actually a palindrome, which adds another multiplier of O(n) time. That leaves us with a massive O(n)(3) time complexity. It's basically a computational villain. It's just way too slow. To put that into perspective, if you pass a string of just 1,000 characters into an O(n)(3) algorithm, you're suddenly looking at 1 billion operations. No way. We need a much smarter way forward. So that brings us to Section 2, finding the inner palindrome. To beat that massive O of n cubed time, we absolutely need a better approach. We can't just guess blindly, right? Let's actually look for structural patterns within the words themselves to shortcut our computational work. Think of the word rotator, kind of like a Russian nesting doll. Palindromes aren't just random letters. They actually contain shorter palindromes hiding right inside them. So the word rotator has otato, which has tat, which has a. It's literally palindromes all the way down. Recognizing this inherent symmetry is the ultimate key to escaping our brute force nightmare. And this reveals a really crucial subproblem. To figure out if a larger string is a palindrome, we actually don't need to recheck the whole thing from scratch every single time. We just check if the outer characters match. So in this case, the R's at the beginning and the end. And then we just peek inside to see if the inner substring, otato, is already known to be a palindrome. If the core is a palindrome and the shell matches, boom, the whole word is a palindrome. This is a game changer because it means we can reuse work we've already done. So we can boil this abstract concept down to 2 incredibly simple mathematical conditions. First, the outer boundaries, the first and last characters, must be an exact match. In code, that's character I equaling character J. Second, the inner string caught between them must also be a palindrome. If both of those conditions are met, we have a match. This logical shortcut ensures we only do the absolute bare minimum amount of checking required as we expand our search. Let's move on to Section 3, the dynamic programming solution. Because we're solving smaller subproblems to build up to our main answer, we can use a super powerful technique called interval dynamic programming to do the heavy lifting for us. We start by establishing base cases where no inner substrings exist. And we have 2 distinct types here. Any single character is inherently a palindrome of length 1, and any 2 adjacent matching characters, like a double C, well, those form a palindrome of length 2. These are the absolute smallest building blocks, and they form the foundation of our algorithm. With our foundation set, we construct a dynamic programming grid. We fill this table by solving for the shortest substrings first. Those lengths 1 and 2 we literally just defined, and then we use those answers to figure out length 3, and so on, all the way up to length n. Think of it like filling in a giant crossword puzzle, where every answer gives you a hint for the next one. By checking the smaller intervals first, we already know for sure if the inner string is a palindrome by the time we check the outer characters. As we build our way up this grid, we meticulously track the starting index and the maximum length of the longest palindrome we've found so far. But here's the catch. Yes, we successfully defeated the ON-cubed time villain. Because we're reusing previous work instead of rescanning everything, we brought our processing time down to a much faster ON squared. However, we accidentally introduced a new flaw, a totally memory-heavy ON squared space complexity. Why? Because storing that giant n by n grid for massive strings is going to quickly eat up all your system's RAM. If you're analyzing a string with 1,000,000 characters, a million by million grid is simply going to crash your system. So we traded time for space, and honestly, we're still kind of stuck. Which means we have to pivot. We must abandon that bulky memory-hogging grid. Instead, we need a leaner, fully optimized strategy that relies purely on dynamic pointers to track our boundaries. We already know the rules of palindromes, and we know our base cases. Now we just need a way to track them that doesn't involve keeping a massive historical ledger in memory. Which brings us to Section 4, the optimized expansion approach. Let's conquer that memory issue once and for all by totally rethinking how we use those base cases. Instead of plotting data on a massive table, we use those single and double character base cases as our starting centers. We iterate through the string, and at every single character, we just drop a left pointer and a right pointer. Then, we simply slide those pointers outward in opposite directions. We check the character to the left and the character to the right. If they match, we expand again. We keep expanding until the characters stop matching. It's essentially like throwing a pebble into a pond and watching the ripples expand outward until they hit an obstacle. And by discarding the heavy data structures and just sliding pointers outward from the center, we achieve a massive victory. Our space complexity drops all the way down to a constant O of 1. We are essentially using 0 extra memory footprint to find our solution. We don't need a giant table, we just need 2 little pointers holding on to our current spot. It's incredibly lean, it's wonderfully elegant, and it completely eliminates the risk of crashing your system due to memory overflow. Let's look at Section 5, Complexity and Final Trade-offs. As we wrap up this explainer, I do want to share one secret pro trick with you, Menasher's algorithm. It's a highly specialized approach that actually finds the longest palindromic substring in an incredibly fast O of n time. It uses really clever string manipulation to avoid redundant checks. But a quick word of warning here. While it is literally the ultimate time saver, interviewers vastly prefer the deep conceptual understanding demonstrated by the expansion approach over you just memorizing tricky, specialized formulas. Menasher's is brilliant, for sure, but the expansion technique shows you actually know how to construct algorithms from first principles. So when we look at the final scorecard right here, the expand from center algorithm hits the absolute perfect sweet spot for your interviews. It gives you a fast ON squared time complexity while maintaining that brilliantly lean O1 space complexity. It is the ultimate balance. We started with a super heavy ON cubed brute force disaster. We moved to a fast but bloated ON squared dynamic programming grid. And finally, we synthesize the logic into a pointer-based expansion that requires virtually no memory at all. Which leaves us with a final thought to ponder. What other complex coding challenges out there could you solve by simply finding the center and expanding outward? Understanding the logic behind these optimizations is the absolute key to unlocking bigger, much harder engineering problems. Keep learning, keep optimizing, and I'll catch you in the next one.